Dear guests, thank you for coming to this session. My name is Ibtihal ABDELMOULA. I'm a research engineer in the Green Energy Park Research and Development Platform. Today, I have the privilege to chair this session about hydrogen system integration efficiency, maximizing the output and minimizing losses. This is the second day of this summit, and by now you should have known that hydrogen is a very promising energy vector for our future. However, there are several challenges that still need to be addressed for an optimal green hydrogen system. Efficiency is one of these biggest issues. So to address these challenges and how to overcome them, this panel discussion will dive into the concept of efficiency in the entire hydrogen value chain and examines the interdependence between stages and components of the hydrogen system. To shed the light on this topic, we are very pleased to have with us 4 eminent experts in the field of green hydrogen. Our first speaker is Dr. Ralf WEHRSPOHN, full professor of experimental physics at Martin-Luther-Universität. He is also co-CEO of the ITEL German Lithium Institute. He holds a PhD from the École Polytechnique in France and worked afterwards as a scientist at many eminent institutes, including Philips Research Labs, Max Planck Institute, and Fraunhofer. Please join me in a round of applause to Dr. Ralf WEHRSPOHN. Our next speaker is Mr. Maurice HANEGRAAF, Business Director, Geoenergy within TNO. He has over 20 years of experience in the field of energy and environmental policy. He is a civil engineer specialized in environmental engineering and public policy from the University of Amsterdam. His research expertise is carbon capture and storage, hydrogen storage, and geothermal energy. Please welcome Dr. Maurice HANEGRAAF. Our next speaker is Dr. Kevin Rouvenhorst, technology expert in Power-to-X at Cullen Industries and the technology manager at the Ammonia Energy Association, aiming to accelerate the responsible use of low-carbon ammonia as a zero-carbon fuel and hydrogen carrier. Please, in a round of applause, welcome with me Dr. Kevin Rouvenhorst. Last but not least, joining us remotely will be Dr. Stefano BARBERIS. He's a researcher at the University of Genova, where he coordinates the Just Green Africa projects. He holds a PhD in turbo machinery and advanced energy systems engineering at the University of Genova. He's also the founder of the Blue Energy Revolution Company, an SME specialized in customized hydrogen systems. Welcome with us remotely, Dr. Stefano BARBERIS, under your applause.
Good morning, everybody. Thank you very much. And sorry not for being here with you.
No worries. So before starting our discussion, maybe we will just have a quick presentation from Dr. Stefano, just 5 minutes presentation, and then we can dive into the discussion.
Yes, thank you very much. And thank you very much also to the other panelists to give me the possibility to briefly present the Just Green Africa project. As you stated, I am the coordinator of this Horizon Europe project. That is a project funded by the Clean Hydrogen Partnership, whose goal is to valorize, let's say, the great potential looking at renewable hydrogen that Africa has. As you know, Africa, thanks to its renewable power potential and low-cost renewable power potential, could have a great capability and a great potential to produce hydrogen with levelized cost of hydrogen at low values, so in values that could be competitive with steam methane reforming. Also valorizing the presence of natural gas infrastructure that could bring hydrogen, for example, to Europe. Indeed, the main goal of the project is to develop mutual benefit roadmaps and mutual benefit initiatives and synergies between these two continents, also to address the need from Europe and from the REPowerEU plan to import up to 10 megaton of green hydrogen in Europe within 2030. But let's say the goal of the project is to develop a green hydrogen value chain in Africa, not only for the export, but also for local demand. For example, the fact that there are different hard-to-abate industries in Africa, if we think about refinery or chemical and fertilizers, so already using hydrogen, and that could decarbonize their production thanks to green hydrogen production. In this sense, the overall objective, as I said, of the project is to develop these mutual benefit roadmaps, but always to keep as focal point this just approach. What does it mean just for the European Commission? It means a sustainable from an economic and environmental and social point of view progress, a progress that has to take into account a fair development of both the continents, avoiding any risk of colonization from, European manufacturer of electrolyzer to Africa just to install. But the idea of the project is indeed to share know-how, share best practices, and create a full hydrogen value chain in Africa, also taking advantage of know-how that is already present. Let me, for example, think about IRESEN colleagues who are one of our partners, and who has their own already experiences from a theoretical modeling, simulation, but also experimental point of view. One other key part of our project is to involve African and European stakeholders, not only, let's say, in training activities that we are developing in the project, and will start very soon from the next month, actually, but also to support us in the creation of this roadmap and, let's say, in the validation of what we are discovering. So the goal of the project at the end is to, let's say, thanks to its 4 pillars that are stakeholder engagement, the modeling results, let's say, that we will perform in different use cases in Africa. The main goal of the project is really to develop own value chains in Africa and develop a fair environment where to collaborate between Europe and Africa, as I mentioned. As I said, in the consortium, we have different partners from both Africa and Europe who are sharing experiences, who are sharing, let's say, modeling tools, contacts, and, we really, really believe that putting together at the same table, at the same in the same project, different capabilities and different experience can make Just Green Africa really the first step towards a green hydrogen transition in the continent. Follow us, follow our project on the website, www.justgreenafrica.eu, and also on our social media. And thanks for the time for briefly presenting the project today.
Thank you very much, Dr. Stefano, for this insightful presentation. So now, my dear guests, we will start with our first topic, which is hydrogen integration efficiency. And as we all know, the successful integration of any renewable energy system as any other system is related to its efficiency. So, Dr. Maurice, we would like to know what are the key factors that contribute to maximizing the output of a hydrogen system. And also, especially if we take each building block apart and not the entire system.
Yeah, thank you for this question. I hear myself. Yeah, this is better. Of course, the efficiency of the whole system requires a holistic approach, but I think we will touch this topic later in the discussion. If you see the cost of the investment cost and operational cost of each step in the chain, then obviously the production costs are the highest. And the capacity factor is of major importance of selecting a location for the production of hydrogen. As you know, we help parties with doing optimizations of wind and solar parks. And it's our experience that if you compare the offshore conditions in the North Sea to Curaçao, which is also offshore, a different type of wind turbine is suited to optimize the performance. You cannot pick the same one. Another example is optimization of the electrolyzer. At TNO, we do research on iridium to reduce the amount of iridium used in the electrolyzer. In the world, there's only 7 tons of iridium available, and that is not enough with the existing technology to fulfill all of our ambitions. The cost of iridium usage is roughly 50,000 to 65,000 euros per megawatt installed. And within TNO, we use ASML printing technologies for chip manufacturing to reduce the amount of iridium in electrolyzers. And we made a prototype of usage with 100 to 200 times less usage of iridium. Of course, we need to make sure that the efficiency of the electrolyzer is maintained. And the last topic I would like to address is the storage. If you look to the natural gas network, then 25–30% of the total volume is you need storage capacity for that demand. For hydrogen, it will be less, but 10 to 25% we think is required. And we're looking to use the subsurface as a large-scale buffer to store the hydrogen in salt caverns or depleted gas fields. Salt caverns can be effective solution, a cost-effective solution, which is can be 100 times higher storage capacity than tanks, and depleted gas fields or aquifers even 100 times. It's not available yet. We have to look in the cost for, especially the reproduction and purification is an issue, but that's a topic, research topic that we are addressing.
Yes, we will cover this topic later in the questions. So you talked about storage, and when we talk about storage, different storage options come to mind. Therefore, I would like to also ask Dr. Stefano, because his research on metal hybrids is very interesting, and it's also a type of storage. So, Dr. Stefano, could you please elaborate on what are metal hybrids and how can they be used in storing hydrogen?
Yeah, metal hydride, let's say, is a way to store hydrogen via solid media. It is a very actually old technology. I would like to say super robust from a technological point of view, but that has been discarded for different years, particularly from the automotive industry, due mostly to its major limit, that is weight. Indeed, the metal hydrides are metallic powder able to absorb and desorb hydrogen, where the hydrogen becomes, let's say, part of this metallic alloy, and therefore these metal hydrides are able to, let's say, store hydrogen even at, I would like to say, normal pressures, meaning pressure lower than 50–60 bar, but even at ambient pressure, let's say, without any specific request of compression work and therefore energy consumption. As I said, they have been discarded in the past mostly by the automotive industry that up to 10–15 years ago was pushing the hydrogen and fuel cell sector, mostly due to their weight, because we have to consider that in 100 kilograms of metal hydrides, more or less we can store between 1 and 2.5 kilograms of hydrogen. But if we look at the system from a volume point of view, the volume occupancy, the footprint is comparable to the compressed hydrogen itself. So in principle, we are talking about a technology that is reliable, that is robust, and most of all, is intrinsically safe. There are very interesting video of the NASA on YouTube that you can see where the NASA researcher fire and shot with a gun against a metal hydrate tank with any risk, even during the, let's say, the blowing out of hydrogen. So particularly for the topic of our discussion, so interactions of different energy systems to maximize the efficiency, what is interesting of metal hydrate is also the fact that during the absorption of hydrogen by the metal hydrates, the metal hydrates release heat, while during the desorption, so while we discharge the hydrogen storage, the metal hydrate requires heat. So we could be somehow able, also thanks to coupling with thermal energy storage or waste heat coming from a fuel cell or even an electrolyzer, to, let's say, properly manage in an optimal way the metal hydrate storage system, thus avoiding any consumption and, let's say, maximizing the efficiency of the power to hydrogen to X solution.
Thank you, Dr. Stefano. And you mentioned heat in your talk. I mean, generating heat and storing heat. This makes us think about heat management in this whole process. So I would like to ask Dr. Ralf, since you are an expert in physics, how can we, I mean, can you explain to us this heat management process and what are the best practices to use in this whole topic in hydrogen?
Yeah, thank you. Thank you very much. I'm perhaps a little bit of what I'm currently doing. So we're working on in the lithium area to decarbonize lithium industry and to related construction areas. And so we're optimizing small industrial park currently. So we're making really business plans currently. And I will speak a little bit about a very specific project where we optimize a business plan. On this side, we have a 20 megawatt rotary kiln to dry stones for construction industry. We might have a fueling station. So we have about 150 trucks there every day, but they're only going in circuits. So they're coming every day back and forth. So that's interesting for changing to hydrogen. We have then office buildings close by. And the rotary kiln, interestingly, only works in construction material area, typically 2,000 hours only a year. So this is a typical system optimization where you're just addressing. And if you just look at the hydrogen part, it's from the business case, okay, but it's not so attractive. It becomes attractive if we take into the case heat and also oxygen, by the way. Oxygen is also important. And only if I take hydrogen, oxygen, and heat together and see this in a holistic picture, it becomes a business case. Because in Germany, one has to say, I mean, the European study from last month has shown it. Actually, it doesn't make sense to make any hydrogen in Germany. Actually, this had zero. That's not true if you look on the business case. That was on a macroeconomic case, yeah, if you look at, but if you are on your own side, it does make sense. And we have optimized this model with an electrolyzer, 7 megawatt, but only if we can take, it's about 1/3 heat. So it's about 2.5 megawatt heat, what we can use in industrial processes and what we can use for the office building. So if you make a whole calculation, so what is the middle? It's wind, and it's mainly wind. Solar is not so much in Germany. It's mainly wind, electrolyzer, industrial heat, partially coming from the electrolyzer, partly by burning hydrogen. And then you can use heating for the office building, the hydrogen for the trucks. And then in the end, it turns out to be an efficient business model. But what we see really is, even though everybody says hydrogen is inefficient because it only has 70% efficiency, but this is not on a systematic peak. If you have a system, heat is actually an important contribution, because the question in future will be, where comes the heat in any way? So the electrolyzer already produces 40 to 30% heat, which is very attractive. So what we do is we optimize really the business case currently, and we are pretty confident. The only question what we have currently is, does it make sense to make the storage on site, or is the storage more interesting to go for a local pipeline? Currently, it turns out a pipeline is a cheaper option for storing than having a local storage system like metal hydride or pipes. But this is still to discuss and might vary depending on the business case. Thank you.
Another crucial component in a hydrogen process is the electrolyzer, and it also needs enhancement in performance. So Dr. Kevin, could you please give us insights about how can we enhance the performance of electrolyzers and also improving their efficiency?
Yeah, so there are multiple things to look at. For example, if you look at a green ammonia plant or a steel plant for that matter, in the process part for making ammonia, you generate a lot of steam. So what you can do with the steam is feed it to a steam electrolyzer, which is more efficient than, for example, water electrolyzers like a PEM, an alkaline, or similar water electrolyzers. So that's an optimization you can make. But also we should look at all the flexibility in the system, because you can produce the perfect hydrogen at full load. But if you're not able to produce on-spec hydrogen during a flexible operation, you're going to waste a lot of your hydrogen in the system. So if you have to ramp down and ramp up when you're connected to a wind farm, it becomes very important over 1 year or like the full operation of the plant. What's the lowest levelized cost of hydrogen? And then electrolyzers that are able to operate with very pure hydrogen, even at low load, so with low crossovers of hydrogen and oxygen to the other side, that becomes quite profitable. And that's also one of the companies within the Colin Industries group. So the Battleizer is developing a fully flexible electrolyzer, which also is a battery. So in that sense, we can operate very flexibly from the hydrogen side, but we can also provide electricity to the ammonia plant, which always needs to be operating at least 10% load. So even when there is no wind blowing, we can be operational, and then you get the lowest levelized cost of ammonia or lowest levelized cost of hydrogen.
So after the electrolysis comes another stage, that's purification and compression. And these two processes are very important to the hydrogen value chain, but they are also energy intensive. So Dr. Ralf, could you give us some explanations on how can we improve the efficiency of these two stages?
Yeah, I come back to this business case was very specific. So if you have an electrolyzer on site, you have the pipeline, okay? You have a rotary kiln where you burn hydrogen, and then you have a storage medium. So first question is, what is the pressure of your electrolyzer it's giving out? If it's zero, there are some companies, even German companies, who started with zero pressure on the output. Doesn't make any sense because the pipeline is on 40 bars. Everything is on between 15 and 40 bars. So first of all, this is very expensive. So first of all, the electrolyzer should be designed in such a way that it's compatible to the pressurized level, because otherwise it becomes very, very costly. And my information is that it's progressing. Everybody is looking that the output is around 40 bar, at least 15 bar, but perhaps 40 bar. So pressure is very important, that the whole system is designed in such a way that you stay on the pressurized level. Obviously, fueling is always at 350 or 700 bar, but on the other areas, it should be in this area. So that's very important, because otherwise business case is not important. Now, more interesting, what we are currently discussing is the purity. Because if you have a chemical process and you're just burning hydrogen, you don't need the Linde standard. This is 99.999. You only need it for the fuel cells, so for the trucks on site. But you don't need, if you burn it, you can just take it directly out of the electrolyzer, no purification. On the other side, if you put it in the pipeline, and that's the question, what is the purity of the pipeline hydrogen? Does it need to be 90, like the chemical pipeline, or has it to be? So that's also relevant for the business case. And I'm really strongly promoting that we go below on the pipeline level, not on the highest standard, because otherwise it's very expensive. If everybody puts hydrogen into the pipeline at this high purity level, cost will be enormous. So purity is still in discussion, in debate. What is the best? For chemical process, actually, you don't need it. You burn it. The truck manufacturers, and that's what I know from Korea, are heavily working to bring down the purity of the hydrogen needed for fuel cell cars and trucks. So they're going to 99.9% now, even lower, because that's the main reason why it's so high. And this is a very important topic we have to do research on. What is the purity on the system? Because even if it goes to salt cavern, you spoke this, I mean, this is a mud. You come out with 95% or so, the rest is water. So all the purification costs are so tremendous, and we need to come up with some standards at least, or some approaches to go away from the Linde highest standard to a feasible standard. So the business cases are important, but that's really research. Can we make electrolyzers or fuel cells which work with lower quality? Can we have what happens in pipelines if the quality is lower? Yeah, is there any problems and so on? There might be reactions between impurity molecules and hydrogen for corrosion issues and force and so on. So there are a lot of questions, scientific questions related to this. Not easy.
You gave me a brilliant transition, Dr. Ralf. Thank you. So coming back to you, Dr. Stefano, and from your perspective and research, how do you deal with these two stages, purification and compression, in the scope of metal hybrids?
Yeah, let's say one of the peculiarities of metal hybrids, by the way, is the fact that they are able to fully purify our hydrogen. So the good point is that once the hydrogen is desorbed from the metallic alloy, it is, let's say, desorbed as more or less 5.0, as Dr. Ralf said. So we are able to avoid any purification before entering our storage, because at the end, the metal, the absorption desorption process is able to perform this purification. By the way, indeed, sometimes metal hydrates are used as a let's say filter, particularly for a very small application. But this is actually one of their property. And at the same time, the possibility to, let's say, have and use a different temperature level of heat to manage particularly the desorption, so the discharging of the metal hydrate storage, could enable to use metal hydrate even as thermal compressor. So even if this is something that has been tested a little bit less than storage application directly, we have to consider that metal hydrates could have this capability. So most of all, another, let's say, good point for metal hydrate is from one side what Dr. Ralf said, so the fact that we can avoid any use of compressor, as I mentioned earlier, and operate directly connecting to the electrolyzer, but at the same time also avoiding any capex and operative cost, any capital and operative cost for purification systems. So this is another good hint for the promotion of the use of metal hydrates, even for stationary application and large scale.
Thank you, Dr. Stefano. Now we move to another topic, which is the efficient integration of hydrogen and renewable energies. And I will ask Dr. Kevin for how can renewable sources be effectively integrated in the whole value chain of hydrogen production, storage, etc.?
So typically, when you look at green hydrogen, there's always an application, for example, a green ammonia plant or a steel manufacturing. So what you always need is hydrogen, and in many cases also electricity. But then if you look at the hydrogen production side, so with the electrolyzer, for example, coupled with a wind farm, what you ideally want to have is hydrogen at pressure, because you would like to send the hydrogen at pressure to the location where the ammonia plant is, for example. And you want it to be flexible. So initially you would think maybe use a PEM electrolyzer, which is quite flexible. The drawback, however, is typically that iridium can be an issue. So there's only so much PEM electrolyzers that you can build. And therefore it's also quite expensive to have these stacks. So ideally you would like to have alkaline electrolyzers. The drawback is, however, if you talk about pressurized systems, the minimum load is something like 30–40%. So if your wind doesn't blow, then you still need to provide 40% of electricity. So that's a lot of batteries. And that's actually where the battleizer comes in. So it has a architecture that's quite similar to an alkaline electrolyzer. But then one of the electrodes is, instead of nickel, iron is used. And by making this smart optimization, we can combine basically an electrolyzer with the battery. And it's basically a pressurized electrolyzer, so you don't need a compressor, because if you think about atmospheric pressure electrolyzers, you need flexible compressors as well, which, you know, is not ideal as well. So with the battleizer, we can be fully flexible, add pressure, send the hydrogen to the pipeline, but also when the wind is not blowing, we could be providing electricity via the battery function.
Thank you, Dr. Kevin. So now we go back to that question at the first, Dr. Maurice. Now, in the light of all these discussions, how can we, if we see from a macroscopic level the whole value chain of hydrogen, how can we, what are the strategies that can be employed to enhance the efficiency from production to utilization of hydrogen?
Yeah, as mentioned before, I think we need a holistic approach, and many sessions in this conference goes about system modeling that also take not only into account the technical aspects, but also the incentives that exist, worldwide policies that exist that have an impact on the business cases that exist. From the Dutch perspective, I think most of the renewable electricity will come from the wind, from the North Sea. And we have the ambition to install, have in 2030, 30 megawatt hours of installed capacity and 70 megawatt hours of installed capacity in 2050. And that is a lot. And on system integration level, the Netherlands is thinking, do we need to bring the electricity to shore, or partly convert the electricity into hydrogen and use the oil and gas platforms and the oil and gas infrastructure that is there. So my expectation is will be a combination of that. And that's a good example on macro level, how such a national system can be developed. But on a lower level, I think you gave a very nice example of the electrolyzers to deliver the hydrogen at pressure to avoid the compression step and things like that. So there are many examples of macro level and system integration at lower level that I think need to be implemented, and that is very much depending on local circumstances.
Thank you so much. So we cannot talk about green hydrogen and its integration into smart grids without boarding the topic of digitalization. So maybe Dr. Stefano, can you give us some hints about how can we improve the process of the hydrogen production using research trends in digitalization, maybe machine learning, data analytics?
Yeah, thanks for this question. You know, as you mentioned, machine learning and data analysis, you know, to operate this, you must have somehow some data to refer to. And you know, we are talking about technologies that unfortunately have not yet, let's say, massively deployed. So we do not have an historical background of data, an historical large amount of data that maybe could be used and could feed these machine learning and AI activities. So for sure, if we would like to furthermore proceed with the development of electrolyzers, fuel cell, etc., particularly looking at the prognostics, diagnostics, etc., I think that we should promote somehow, for example, an hydrogen data space in Europe, in different European funded research projects. We are promoting this idea of data spaces where we can share know-how and data directly from demonstrator, directly from prototyping. I think this is something that we should do also for fuel cell and hydrogen technologies. I know there are still some industrial secret, maybe not to be disclosed by the manufacturer, but I hope that at least among us in the academic sector, there could be maybe more openness to share tests data, experimental results, particularly to facilitate the possibility to develop some machine learning activities and digitalization-based activities.
Thank you, Dr. Stefano. Yes.
Yeah, I might like to add on this point of digitalization. I think that's very important. I think for most of the component electrical grid, we have a digital twin. Let's call it digital twin that exists. And Microsate and the big companies in Germany, Siemens, they have digital twins, MTU or whatever. So MAN Energy, so they have digital twin of the microgrids. The trouble with the electrolyzer is nobody knows the exact specifics on lifetime, for example. What is really the lifetime issues on the long run? Okay, so a research topic is clearly that actually we need for each electrolyzer a decent electrical twin so that we can make optimization of the system and the scenario. And this is not that easy, yeah, because it depends on the load regime. We spoke this, yeah, the lifetime or the critical issue. So that is research ongoing. Actually, you need this digital twin for each electrolyzer. So there's still room for research together with companies to do this. And once we have this digital twin, we can make with the other tools, I think is done. This can be done optimized and on the system efficiency.
Yes, sure. So to sum up, could you please give the audience some successful use cases, each from, for example, from Germany, Netherlands, Italy, and some use cases that will also benefit us since we are talking about green hydrogen roadmap in Morocco. What are the lessons that you have learned from your specific use cases that we can use and benefit from? Maybe you start with Dr. Kevin.
Yeah, so actually I do not want to focus on Netherlands. We have the BARBERIS in our group, but also Proton Ventures, which is currently doing a EPC project with UM6P and IRSN for a 2x2 megawatt electrolyzer plant. So there's an alkaline and there's a PEM system, and then a small scale green ammonia plant. And so the idea of this plant is really to look at how does a flexible ammonia plant on a larger scale work. And I think this is a very nice example of a collaboration between Dutch companies, also with the Moroccan market, because in the end, a country like Morocco has the optimal conditions for solar and wind. So, I mean, we can develop a lot of hydrogen projects in the Netherlands, but probably it makes a lot more sense to develop a lot of green hydrogen projects in Morocco and have all the industry here as well. So, for example, OCP in Morocco is importing something like 2 million tons of ammonia currently, which is equivalent to 2 of the largest ammonia plants in the world right now. So I think there is a current captive market we can tap into, and it's not just Morocco developing its own thing, Germany developing its own thing, the Netherlands developing its own thing. It's really about collaborating all across the value chain, all the way from human capital at the universities, so collaborations over there, all the way to industrial applications.
Yes, so maybe that's a great summary of your use case. Maybe you could follow on a Netherlands use case, or
yeah, I really support your words that you just said. So let me have two examples. One example from the Netherlands is the use of waste heat by the electrolyzers that will be fed into the district heating systems in the Netherlands, in the Rotterdam area. I think that's a very nice example how to improve the business case. And I think you also mentioned this example. The second example, again from the Netherlands, is the installation of an electrolyzer on an oil and gas platform in the North Sea, where the system integration between the old world, the gas, and the new the new gas is being mixed and can enhance each other. And the final point I would like to make is the storage capabilities. We have reviewed also Morocco, the subsurface in Morocco, and we see that there might be possibilities for large-scale storage applications in salt caverns, in aquifers. The data is scarce, but we are more than willing to look for opportunities together with Moroccan partners to see if this could be strengthening the case here in Morocco.
Thank you, Dr. Maurice.
Yeah, I might continue. Yeah, I think when I started this 2010, we started a big hydrogen cluster in Germany. We're very motivated. Yes, we can make hydrogen by ourselves, but actually the grid, the electricity price, in particular, the grid costs are so expensive in Germany now that the European Union just said it officially doesn't make sense to make any hydrogen with the grid costs we have currently. It's no business case, no business case. So the only business case is off-grid, so avoiding the grid cost I spoke about an example. So my recommendation to Morocco is, and you have also pretty high grid costs here, don't increase the grid costs too high, because otherwise you run into the same trouble as Germany and the prices get too high. Then you have to also own your off-grid parks, and they are much more complicated in the business model. So keep the grid costs low in Morocco and don't overload.
We don't have the minister with us.
Yeah, but it was just recommendation from Germany, Morocco. Keep them low, and don't sell the grid to private investors. We did it, and so on and so forth. So this was all lessons learned. I don't know how we sort this out in future, but this is the critical path here, and so hopefully Morocco doesn't need to make the same mistakes. Thank you.
Thank you so much, Dr. Ralf, for these recommendations. Dr. Stefano, could you add a use case from Italy?
Yeah, maybe just one word also from the lessons that we are learning in Just Green Africa project. As I mentioned during my initial speech, in Europe, we are talking a lot about hydrogen valleys, and even in Italy, so trying to create an intersystemic approach to promote hydrogen. What we are learning in Just Green Africa is mostly that due to the different situation of countries in Africa and in Europe, I think we should have a different approach. I fully agree with what was stated earlier about possibility to take advantage of large industrial plants that already have, for example, all the facilities to manage large quantity of hydrogen, and that today are self-produced by steam reforming mostly. So I think for sure for Morocco, the first target for promotion of renewable hydrogen is to take advantage of this large off-taker, and starting from these large off-takers, maybe create all around this big hydrogen hub, as we call it in Just Green Africa, further demand that could be even at general audience level with buses or whatever else. And another suggestion could be maybe to make a thought about ports. You have Tangier ports, but not only, even other ports that are could become hubs not only for export, but even for the usage of hydrogen at local level. In Italy, we are working a lot on this topic, particularly to use fuel cell equipped special operating vehicles, locomotives, etc. And I think this is something not so difficult to be implemented in whatever port in the world. So these are my 2 cents.
Thank you so much to you, Dr. Stefano, as well as Dr. Ralf, Dr. Maurice, Dr. Kevin. Thank you for this fruitful discussion and insightful discussion. And I guess we are just in time, so maybe we can conclude this fruitful session. And thank you very much, dear audience, for your presence. And if you have any questions to our esteemed guests, maybe in the break, you can approach them. Thank you so much.